Welcome on this last lecture of this online course Physics with Scilab. Today on this 17th day of this online course, I am going to demonstrate the modeling of the electrical or electronic circuits in Xcos. For the modeling and simulation of electrical or electronic circuits, we are using electrical palettes or blocks available in the palette browser of Xcos. To use these blocks from the electrical palette, it is necessary to have a C compiler installed in the machine. So before starting the modeling in Xcos, you need to check that whether C compiler is installed in your machine or not. Otherwise, you have to download the GCC compiler. Again, you need to install MinGW module from Scilab. It have an access from application module manager atoms, in which you found the window tools, and from there, according to your requirement of a machine either of 32-bit or 64-bit, you can install the MinGW module. This MinGW module will make the link between Scilab and GCC compiler. To check whether this C compiler installed in the machine is linked to the Scilab, just type have a compiler command in the console. If it returns with true, then there is a link between Scilab and the compiler, and if it returns with false, that means there is something wrong. Today we are going to model these four circuits using operational amplifier block in the electrical palettes. Now I have opened my Scilab environment. I have already installed C compiler in my machine. I also have installed MinGW module from Scilab. Let me confirm that whether C compiler is linked to the Scilab. To check, I use command have a compiler. So it returns true. That means it is linked. Now to launch the Xcos, I click this icon. So here are two windows, the palette browser and Xcos editor window. Now I am going to draw this first circuit of op amp as a inverting amplifier. So for this I need an op amp, two resistors, then two ground blocks. I can get these blocks from the palette browser, from the electrical palettes. So first I will take this op amp block. I positioned it here. Then I need two resistors. First and then second one, two ground blocks. Again I need a input voltage source for amplifier. I choose this sine voltage. To measure input and output voltages, I need two voltage sensors. So these are the voltage sensor blocks. first and then second. Now I am connecting the ports of these blocks. Before that, I am positioning these blocks at a proper place. I will rotate this source by this rotate option. Now I am connecting the ports of these blocks. The input and output voltages are to be measured with respect to ground, so therefore one terminal of this voltage sensor is connected to the ground. Also, this non-inverting terminal is connected to the ground, so I will connect it to here. The input and this port to the sensor. Now you can check the circuit whether the connections are correct or not. So this is the RF resistor, this is R in resistor. So input is given through this R in resistor, and with respect to ground, the non-inverting terminal is grounded by this path. The output voltage is measured with respect to the ground. Input voltage is also measured with respect to the ground. These sensors will sense the voltages but can't show the numerical values as does in usual voltmeter. So I need scope to see these voltages on the graphic window. So therefore I am using this C scope, which has two inputs, so that we can use it to see both the input and output voltage waveforms. This can be optimized also in this way. Now the output voltage to the scope, event input for the scope, the clock, now I will set the parameters for the blocks. I will keep this 1 volt. I will set this value to 1000 ohm. This is also I keep 1000 ohm. Now this is the parameters of the scope. So I will set Y minimum for both -2 and Y maximum for both the scopes 2. So time base for the scope I will adjust to 0.01. Now this diagram is ready to simulate. So I will go to start. So now the graphics window appear on the screen. So it is showing both input and output of the amplifier. So this is the input shown by a black waveform and the green waveform for the output. Since this is an inverting amplifier, input and output are 180-degree out of phase. Also, it can be seen that the amplitude of both input and output waveforms is same. Since we have set this both resistance to 1 kilo ohm, therefore the gain of the amplifier is -1. I will change the value for this feedback resistor to 2 kilo ohm, and now I will start the simulation. So this is the graphics window. Now you can see the gain of the amplifier -2. Minus because the input and output waveform are out of phase. So in this way we have create the simulation for the inverting amplifier. The same circuit diagram for the inverting amplifier, but the connections are made in a different way. Here I have used the DC input for the amplifier instead of the sinusoidal voltage which we have used in earlier circuit. So the parameters: the 1 volt DC input, the resistance is set to 1 kilo ohm. This feedback resistance also set to 1 kilo ohm. So this is dual input scope. Its Y minimum is -2 for both the inputs and Y maximum is +2 for both the inputs. The clock parameters: the voltage sensor, it is measure the output voltage with respect to ground, and this voltage sensor will measure the input given to the inverting terminal through this resistance with respect to the ground. So now I will start this simulation. So this is the graphics window showing the output of this inverting amplifier. So this is the input that I have given, that is 1 volt, and the output is -1 volt because the gain is 1, and as it is an inverting amplifier the output is inverted. Now I increase the gain. Suppose I set this value of IF to 2000, and now I will start the simulation. Now the gain becomes -2 because here this is the output voltage which is equal to -2. Now I will make some changes to get this non-inverting amplifier circuit. The number of components or blocks that I needed is already there in this window. I just need to rearrange the connections. Now this diagram is complete. I will set the parameters for the scope. The parameter for second input to the scope I have set to the -4 and +4. and this value again I will set to 1000 ohm. Now run the simulation. So this is the input, which is 1 volt DC, and this is the output for the non-inverting amplifier. So as its gain is 1 plus RF upon RI, so RF and RI is same, so ratio is 1, so 1 plus 1 is 2, so the gain is 2, therefore output is 2. And since it is non-inverting, so both input and output are positive. I set it to 2000. So now it is 3, because 2 by 1 is 2 plus 1 is 3, so gain is 3. This is the integrator circuit using the op amp, which is shown in the figure. So here there is a capacitor in the feedback, and the output of this integrator will be integration of the input. So for input I have used this 0.8 volt sinusoidal voltage generator. So I have set its frequency to the 200 hertz. This capacitor I have set to 1000 nanofarad, means 1 microfarad. The scope parameters for first input -1 to 1, and for second input -1 to 2. Okay, so now it is ready. I will start the simulation. So this is the graphics window showing the output and input. This blue waveform is the input and this red waveform is the output. So it can be clearly seen that there is a phase difference of 90° in the input and output waveform, as the integration of sign is minus cos, and since the circuit is in inverting mode, so there is again minus, so minus minus will get cancelled, so net phase difference is 90°. You can set the different values of this input resistor and this feedback capacitor. Also you can change the frequency of the input signal. Now this is the circuit for a differentiator using operational amplifier. There is a small change in differentiator. The positions of capacitor and resistors are interchanged here. So same input I have used. The scope parameters also I have kept same. Now I start the simulation. This is the graphics window. So here also you can see the input waveform, output waveform, and output is the differentiation of the input. So you can see the input is a sinusoidal signal and output is a minus cos signal. You can see the variation in the amplitude of the output waveform with the frequency and also with the values of the resistance and capacitors. So in this way we can create the different circuits in Xcos and we can simulate those circuits. You can also use the different colors for the blocks in this way. You can also change the background of the window in this way. So all the changes can be saved. In this diagram I have used the some mathematical blocks. So this is a sine wave generators, and these are the gain blocks. With this we can adjust the amplitudes of the sine waves. So these blocks will add the three inputs, set the frequencies for 10, 30, 50, 70 and 90 odd harmonics, and the corresponding amplitudes are 1, 1 by 3, 1 by 5, 1 by 7 and 1 by 9. The resultant of these waves should be a square waveform because it forms a Fourier series for square wave. So let's see. Okay, so this is like a square waveform. In this way you can create any mathematical model also in this Xcos. Some Xcos demonstrations are also available in console. You can explore many aspects of the Xcos using these demonstrations. For example, this is the demonstration for the bridge rectifier, which is available ready-made in the Xcos. Input and output waveforms for the bridge rectifier circuit. That's all for this last day of this course. I hope you have enjoyed this course. At the outset, I must thank to all of you for your response to this course. I'm also thankful to the management and the principal of the college to allow me to conduct this course.